Hi there, welcome to our second lesson. Now, for a moment, we put the philosophy of risk on the side. We will be back several times during the course and in particular at the end of the course. And we consider risk from a different perspective. So today we will introduce risk measures, and to play with risk measures, we will start by using the so-called axiomatic approach. So we will first give a definition of risk measure from a mathematical point of view, and then we will list a series of properties that we would like our risk measure to have. Now, not all the different risk measures we will consider together will have all the properties we consider in this lesson, but that is not important. You will see that actually having all the properties is not what we really need. There are some properties that are somehow more important than others and that should not be dropped if you want to do if you want to make a correct assessment of risk using these risk measures. Other properties can be more or less useful, and I will try to convince you of that. But in any case, it is always very important to know what are the properties of the different risk measures we can use. Because you can never cry ex post because your risk measure was not performing as you were thinking it would, just because you ignored that your risk measure was not or is not subadditive, or is not coherent, or is not convex, and all the other things that we'll see together. During the course, you will see that I will stress a lot this thing. It is never the fault of the tool that you use. It is always your fault. Because every statistical tool you might use for any purpose is a tool, okay? So, with a fork, you can do something, but you can also do many other things. I mean, you can always stick a fork in your hand. It's your choice, okay? So, if a statistical tool does not work, there are many possible reasons. Maybe the data are not good. And then it is your job to try to find better data or to clean the data. Maybe the data are not enough. And again, you try to augment, to increase the number of data that you have. But for sure, a tool will not work if you ask the tool to do something that it is not supposed to do, or if you ask a tool to have properties that are not inherent to the tool. So it's very important to know what are the objects we are playing with. So let's start. Now, our job as risk managers is to manage risk. Okay, this is some sort of tautology. But what does it mean to manage risk? Now, if you want to list what are the different goals of risk management, I like to say that there are mainly four. The first goal of risk management is to identify risks, to identify the possible sources of risk. So before being able to evaluate a given type of risk, you have to be able to say what is a risk and what is not for you. Okay, so the first goal is to identify. The second goal is to assess. Okay, so we have to quantify risk. We have to understand if something is riskier or less risky than something else. Given this knowledge, so given the identification and the assessment, the third goal of risk management that will also be reflected in the properties that we will require for the different risk measures is to be able to rank risks, to prioritize risks. That is to say, we want to be able to build a ranking of the risks and to be able to say that this is riskier than that, this is riskier than this, and so on. Why that? Because unfortunately for us, in the real world, when we play the role of a risk manager, we don't have all the nice things that we have, for example, in financial mathematics. In financial mathematics, if you remember in the course, I told you that we are beautiful and dirty rich. So we don't care about constraints. We can do whatever we want. Okay, in risk management, this is not the case. We have constraints. So if we want to cover, if we want to hedge for the different risks, we have a limited amount of resources. We have a limited amount of capital for doing that. So we have to decide what are the really important types of risks for us, those that we will try to hedge. So it is fundamental to be able to rank risks. After identification, assessment, and ranking or prioritization, what we have to do, we have to hedge. So we will have to build strategies in order to cover for the different risks. Now, in order to do that, we need tools. We will see that the tool that we can use to identify and to assess, so to quantify, are actually risk measures. Now, risk measures, prosaically speaking, are nothing more than tools that allows us to assign a number, a letter, any type of tag to the different types of risks. Given those tags, we can, for example, build a ranking. And so we have the third goal of risk management. After doing that, using the same risk measures, using other risk measures, or using strategies that we will see together, we can try to hedge the different types of risk. Later on in the course, for example, we will see that there are situations actually like those under the Basel framework in which the strategies that we will use to hedge risk are somehow already decided by the regulator if we choose to use some of the approaches proposed by the regulator. So let's start by playing with risk measures. So let's try to give a proper mathematical definition of what a risk measure is. Now, let's consider the standard financial mathematics setting. So we are considering a market, and for this market, we just focus our attention on a given time horizon, that is the interval 0, capital T, where capital T in financial mathematics represents maturity, but for us is essentially the limit time horizon for our risk management evaluations. So for our hedging strategies, for determining the different types of risks, for assessing them, and so on. For what concerns the description of the market, we will use the common triplet. So we will use the probability space, omega, f, p, where p is the physical measure. As I told you in the first lesson, a very important difference if you want to use risk management in practice and if you want to really be a risk manager and not just speaking about risk in purely theoretical terms, what is important for us is that most of the times we will play under the physical measure and not under the risk neutral measure, as it is the case in financial mathematics. Okay, we will use sometimes the risk neutral measure, but it will always be an intermediate step for maybe having simpler computations to get some auxiliary results, and then we will always try to come back to the physical measure. So also tools that we have already briefly considered in financial mathematics, like distortion functions, like distortion probability measures and distortion risk measures, will be back in our course because they can represent a way of switching between the risk neutral measure and the physical measure. So of moving from one measure to the other according to our necessities. By the way, if you do not recall the definition of distortion function, distortion risk measure, and so on, please have a look at the link that appears now on the video and that refers to the lesson in financial mathematics in which we are playing with those objects. Our risk measure is meant to quantify the amount of capital or assets that we need to keep as a reserve. The aim of a reserve is to guarantee the presence of sufficient funds that can be used as a partial cover if a given loss manifests itself. Even if we will not enter into the details here, too formal and theoretical for us, in risk theory one can define the so-called acceptance set as the set of all the outcomes of an investment that are acceptable for an agent. In this framework, a risk measure determines the amount of capital that, added to a given outcome, makes it acceptable to us. This does not necessarily mean that we want to fully cover a loss to make it acceptable, but that, following our risk preferences or some external regulatory impositions, we are able to at least partially deal with it. Given our probability space omega fp, let L of omega fp be the space of all the random variables that are almost surely finite. We can then consider a subset L which will represent all the possible portfolio losses over the time horizon 0 capital T. Please notice that when we say losses, we mean losses and profits. But since we are risk managers, to simplify notation, for us losses are positive values and profits are negative. A profit is nothing more than a negative loss. In other words, we use the loss and profit distribution instead of the commonly used in asset pricing profit and loss distribution. A real loss has, for us, a positive risk. That is to say that we need a positive amount of capital to deal with it. A profit, that is a negative loss, has a negative risk. In fact, we do not need extra capital to cover it. Even more, we can withdraw capital. It goes without saying that cash has no risk for us if we assume that inflation is negligible in the interval 0 capital T, the risk associated to cash is also negative. If we can add cash to a risky position, actually we will decrease risk, as we shall see in a minute when we consider the property of cash invariance. From a mathematical point of view, we assume that the set L, that I repeat is the set of all the portfolio losses that we can experience over the time interval 0 capital T, is a convex cone. In other words, we are simply assuming that if we have two losses belonging to our set L, then if we sum them, their sum is still in the set. And if we inflate losses by multiplying them by a constant, then the result is still in the set. So it's just the standard convex cone that you recall from linear algebra. Now, once we have these, we define a risk measure nothing more than a real valued function ρ that maps from L into the reals. Now, we will require this measure to satisfy a certain number of properties. A coherent risk measure is a risk measure that is monotone, translation invariant, positive homogeneous over the one, and subadditive. Some risk measures can be either coherent or not coherent, depending on the definition of the convex cone L. Now, monotonicity implies that we can rank risks, and that for higher risks we need a larger amount of capital to build a reserve. So this is a very basic and intuitive property that we want our risk measure to satisfy. Translation invariance tells us that if we consider a risky asset or portfolio and we add a non-risky asset to it, say cash, then the risk will not increase. Even more, it can decrease, given that the added cash can already play the role of reserve capital. Now, since cash invariance can be defined with or without the plus b term on the right-hand side of the equality, we put that into brackets for the moment. Depending on the risk measure that we will consider, we will require cash invariance to be just the equality without the plus b term or the equality with the extra plus b term. A risk measure that is monotone and cash or translation invariant is also known as a monetary risk measure. We can then ask our risk measure to be positive homogeneous of order 1. This implies that if we double an investment, the related risk should also double. We shall see that this property, positive homogeneity, while easily understandable and, in a sense, intuitive, it is trickier than what it may seem. Finally, we have subadditivity. Subadditivity is the property that fosters the diversification of risk. If a risk measure is subadditive, the risk associated to a portfolio of assets is lower than the sum of the risks of the single assets. It is easy to observe that if a measure ρ is monetary and subadditive, then it will necessarily be negative for negative losses, that is, for profits, perfectly in line with what we have said before. So, just to summarize, monotonicity from a financial point of view means that we are able to rank risks. So we can build a ranking, and this is something that we want. Cash invariance or translation invariance means that if we add a non-risky asset to a portfolio, the risk of the portfolio should not increase. And we will see in certain situations will also decrease. So not only it will not increase, but it will actually decrease. Then we have positive homogeneity. This allows us to say that somehow there is a proportionality in risk. And if we double a portfolio, we are essentially doubling the risk that is linked to the portfolio. Again, I repeat, this can be tricky, as I will try to stress in a minute. Finally, we have subadditivity that in financial terms is nothing more than requiring diversification. So for a coherent risk measure, we are essentially asking that our measure is able to foster diversification. It will push us to not put all our money in just one type of asset, because if we diversify our portfolio, the overall risk might decrease. So if we want to verify that a given risk measure is a coherent risk measure, we have to check the different properties and see if the measure satisfies the properties. Now, on the course website on Brightspace, you find, for example, a very short note I wrote for you showing that if we consider two very basic risk measures that we all know, that is to say the standard deviation and the variance, it is extremely simple to show that the standard deviation is a coherent risk measure while the variance is not. The standard deviation satisfies all the requirements, so monotonicity, positive homogeneity, translation invariance, and subadditivity, while for the variance this is not true. In particular, it is very simple, I guess, to observe that the variance is not positive homogeneous of order 1. If I have a random variable x and I compute var of x to be the variance, if I multiply the variance by a constant, say a, then the variance of the new variable ax is not a, the variance of x. That would be what we need for positive homogeneity of order 1. But conversely, we get a square, the variance of x. So immediately we see that this property is not verified. Moreover, we can very simply check that the variance is not subadditive, while, to our surprise, sometimes the standard deviation is. And here you already see, for example, one of the reasons why, in speaking about volatility, in trying to model volatility, we prefer to use the standard deviation with respect to the variance. The reason, one of the reasons, is that volatility is coherent, while the variance is not. So, even if one measure is just the square root of the other, there are big differences from a risk theoretic point of view. So I repeat, you will find a note with all the details. Later in this lesson, we will also introduce other risk measures, for example, the valid risk and expected shortfall. The valid risk is not, generally speaking, a coherent risk measure, while the expected shortfall is. Why am I saying that the valid risk is not, generally speaking, a coherent risk measure? Because the valid risk can be coherent in very specific situations. Like, for example, if we assume normality, or if we assume that our portfolio is of a certain type, for example, is a comonotonic portfolio. Now, I think that it is already interesting to say something about this fact of the VAR being or not being coherent, because it is one of the problems of the valid risk. So the valid risk has been used and abused a lot in risk management, because you will see it is actually a nice measure of risk. But a lot of people have assumed the valid risk to be always coherent, and this is not the case. And this assumption has actually, like during the crisis of 2007-2008, generated problems. But again, the problem is not the problem of the measure, because we know that the valid risk is not, generally speaking, coherent. It can be. But what's the point? For sure, it is coherent under normality, and if you assume a model in which normality is the only type of randomness you can play with, in which the only type of dependence you can play with is linear dependence, and so if you go multivariate, you will play with the multivariate normal or the Gaussian copula, then for sure the valid risk is subadditive. But then reality kicks in, and then you discover that the valid risk you have computed is not reliable. Maybe it is largely underestimating risk. But what's the problem? Is the problem of the valid risk not working, or is the problem that you were using the valid risk in a situation that was not normal because you wanted the measure to be coherent, yet normality was not verified in the setting you were considering, and it was just your theoretical construction with no actual link to the real world? Again, it is never the problem of the measure, it is always the problem of the risk manager using the measure. Okay, so in the second part of the class, we will discuss valid risk and expected shortfall, and also towards the end, we will see how to use these measures in R, for example, using some real data, and we will see that coherence with real data is not so verified, because subadditivity typically drops. So the problem with the valid risk is that the valid risk typically is not subadditive. Now, coming back to our axiomatic treatment of risk measures, for a coherent risk measure, we have required 4 different properties. Now, it is not difficult to see that positive homogeneity of order 1 actually is a tricky requirement, because essentially we are just asking that if we double the investment in a portfolio, then the risk doubles. If we triple the investment, then the risk triples, and so on. So every time we increase the amount of money in an investment a certain number of times, like n times, then the risk increases n times. Now, from a risk management point of view, this is actually not very clever, because we would like to have a risk measure that does not foster concentration risk. Concentration risk is the risk of having all our money, all our investments in just one asset or one portfolio. Why is that a risk? Because then if things go bad, they really go bad for us, okay? And we cannot diversify, so we cannot hope to have, for example, some gains from some other portfolio to at least partially compensate losses. So since we know that it is very intuitive, we know that we want to diversify risk, we don't even need the economic and financial justifications that are fundamental from a theoretical point of view. But I mean, it's really intuition. It's your grandmother's wisdom that it's better not to put all your money in just one investment, but to diversify. Okay, positive homogeneity actually in this enunciation, in this format, fosters concentration risk. And once you have concentration risk, then you also have liquidity risk, because imagine that you have all your money immobilized in one type of asset, and you have to liquidate the asset, then we will see that you can enter into the realm of liquidity risk. So you are not able to liquidate the asset at the conditions you want, or maybe you are not at all able to liquidate the asset. So you have something that cannot be transformed into cash in a decent amount of time. So we will be back with liquidity risk in any case. It's quite important in the Basel framework. Okay, so we have a measure that is coherent, and since it is coherent, it is positive homogeneous, and being positive homogeneous, it somehow favors concentration risk. So we don't want that. So what we can do, we can drop positive homogeneity. Obviously, the measure will no longer be coherent, but we can always find another name. The problem is that if you drop positive homogeneity, immediately you also lose subadditivity. Why? Because a way of dropping positive homogeneity is to remove the equal sign. So to say that rho of AX is no longer equal to A rho of X, but we can say, for example, that rho of AX is larger than A rho of X. In this way, by increasing our investments in one single type of asset or in just one portfolio, we see that our risk increases more and more because of dropping positive homogeneity. But if you assume that, then subadditivity is immediately violated, because if assume that I have one investment and this investment can generate a loss L. Okay, I can always compute the risk of that loss. Well, that would be rho of L. Now, if I double the investment, I can have rho of 2L. And what I want is that rho of 2L, if I drop positive homogeneity, is larger than 2 times rho of L. But I can always write rho of 2L as rho of L plus L. But then what do I have? I have the rho of L plus L is larger than 2 rho of L. Okay? Now, 2 rho of L can be written as rho of L plus rho of L. So at the end of the day, what do we have? We have that rho of L plus L is larger than rho of L plus rho of L, which is the contradiction of subadditivity. The solution to this problem is to also drop subadditivity and to substitute subadditivity with something else. The new type of risk measure that we will get is no longer a coherent risk measure, but is a convex risk measure, which is very, very flexible, very, very useful, and we will see through the course that many of the risk measures we can play with are actually convex. To obtain a convex risk measure, we introduce a convexity requirement for the measure. That is, the risk of a linear convex combination of losses is lower than a linear convex combination of the single risks. If the equal sign of positive homogeneity is replaced with a larger than or equal to sign, then a coherent risk measure is convex, while, please observe, the opposite is not necessarily true. A further relaxation of convexity is quasi-convexity, in which the rho of the convex linear combination of L1 and L2 is smaller than equal to the maximum between rho of L1 and rho of L2. As we shall see, quasi-convexity is a property of several scale-free risk measures, like, for example, the Gini index.